We need something else. We need a radically different picture than this. And this is where we come to the quantum mechanical model, the quantum model of the atom. And the quantum model of the atom, I mean, it's just out there. I would say that it's the most successful theory we know of in physics today. So let's go look at this thing. The quantum model of the atom. So what can I say here? Quantum physics is the science, and it's really the science of the subatomic world, the science that has very successfully and completely described the behavior of the atom. Part of quantum mechanics is a theory called quantum electrodynamics, and it has the ability to predict things to 12 significant, digits, numbers. It is outrageously good. And what you're going to see here is that there's really two models here that people confuse. There's what's called the Bohr model. And the Bohr model is what we call a semi-classical theory. And what it does here is when I say the word semi-classical, that means most of it is actually Newton's laws. And just a tiny bit of it is quantum. So it's a mixture of two. But this Bohr model, what I would call this here is that this was a Band-Aid on a cancer sore. It was not an answer to the atom. It was the first attempt. And what you find here is that now you have electrons in orbits, but he could not explain why electrons did not radiate energy. And that's what I mean by it was a Band-Aid on a cancer sore. Even in the Bohr model, they knew that the electrons in some strange way could not radiate energy. And so these orbits, so what you find here is that for the first time, these orbits now comes up this thing called energy levels. And so what you find here is that the Bohr model is the stepping stone. What's really there is the quantum model. And the quantum model only uses energy levels. And it is the quantum model that is the model here. And what you find here is that there's something really strange about the quantum model. So in quantum physics, electrons live in energy levels. Bohr still thought that the electrons lived in these orbits. But you're going to see, though, is that as soon as you say energy levels, that it's a radically different picture of the atom than one thinks about electrons moving in circles. So just to be really clear here, when we talk about energy levels, I don't really mean it's not shells and it's not orbitals like people think about when they say energy levels. A lot of people who have taken chemistry will say, well, they're one and the same. And I'm going to say that, no, they're not. And another thing that's really strange here, electrons live in energy levels and they jump between levels. And that's a really strange concept here. So now that we kind of compared these two models, it looks something like this here. So what I'm going to do here is that I really need to have an analogy for energy levels. So here's my analogy for energy levels. And this is a pretty standard analogy. And this is called a flight of stairs. I mean, of course, you know everything about going down the stairs. And what we find here is that it goes something like this. When you walk, right, down the stairs, of course, your foot can only land on the stair, the tread, never the riser. So what do I mean? So when I look at a stair, here's what we mean by this. This piece right here is the tread of the stair. And so for the sake of simplicity, I'm going to call that the stair. This piece right here is the riser. Your foot will never be able to rest on a riser. So when I'm looking at this thing, I'm seeing, right, we're walking down some stairs here. And so when you're thinking of the stairs, again, here's the stair part. That's the only place you can walk, not the riser. So as your foot is landing here, right, as your foot is landing here, what you're seeing here is that your foot lands on the stair while your other foot is in the air. Right? So clearly what we say here is that this is the only place a foot can land. Your foot will never, ever land on a riser, right? Never. So then if I take this to the quantum model, it essentially says the same thing about atoms. So in quantum physics, states that electrons in atoms can never be in between energy levels. And what I mean by that is that we say that an energy level is the step or the stair, and the riser is, excuse me, so in between energy levels, we call that the riser. So then if I look at this thing to try to make the transition here, I'm going to look at a ball moving down the stairs. So suppose a ball moves down the stairs. So if I look at this, I have my stairs now. And what you're seeing here is that there's some language now. So if I think about this, here's what we say. And this is where it gets really strange here. 1, 2, 3. So there are 3 energy levels which are represented by the stair. The first one is called the ground state. And the ground state, what we say here is that can never, ever be 0. And that's a pretty hard comprehension. And the reason why is that a lot of times we could just say, well, if something's just sitting there, its energy must be 0. That turns out not to be true. So then what we do here is that we come in and we then say, okay, so this guy right here is what we call the first excited state. This guy is the second excited state. And so it goes on and on and on. So what you're seeing here is that imagine that I have a ball here. And when I think about a ball, I'm kind of thinking that now we're replacing the ball with an electron. And when you look at the electron, there are multiple paths to go to the lowest energy state here. And what we find here is that all systems will always move from higher to lower energy. And that is absolutely the case in the atom. And so what you're seeing here is that you could see this. So the electron or the ball, to get all the way to the lowest energy where it wants to be, well, when you look at this thing, what you're seeing here is that it's making a jump from the third to the second, from the second to the first, right? So this is going from 3 to 2. This is going from 2 to 1. But then there's another path that it could take. It can actually take a path all the way from 3 to 1. So there are multiple paths that the electron can take to get to the lowest energy here. So now, how does this translate into the quantum model? Maybe I should not write it like this. Now we have the quantum atom. And when you look at the quantum atom, I look at these energy levels, and we then come in and we go like, okay, here's energy level 1, 2, 3. So this is 1, 2, 3. And if I want, I could have 4, depending on the atom. You'll see that it's only the structure of the atom that determines it. So these guys right here, these are the energy levels. And that's what I mean by the stair. And if you look right here, this is the riser part. No electrons will ever, so this tells us here is that no electrons will ever be in between energy levels. And nobody has ever seen them. And when you look down here, you could see here is that this guy is the ground state energy. Not equal to 0. And this is one of the big surprises is that, again, I've said this again, but there's no such thing of an electron or an atom with 0 energy. It doesn't exist. And so here's what you want to think about. So this is the picture of the atom. This is what an atom looks in the quantum mechanical model. Not this. Okay, not this. This is the atom right here. So this is the best picture of the atom. And you know what? I'm gonna bring this down a little bit because I want to draw one more thing. So you might say, wait a minute, what about the nucleus? The nucleus is right here. Even though it's customary not to draw the nucleus here, I will draw it here because that's where it's at. And so this little guy right here is the nucleus. And this is the picture of the atom. I know I've had people tell me that's not a very satisfying picture. I don't care. The fact is that this predicts the behavior of the atom better than anybody else, better than any model. So that's what the atom looks like. Crazy, right? So if I come back and I get this image here, and I bring this back down, this is not what the atom looks like, right? This is not what the atom looks like. This is a bad model because its predictions are very poor. Now, we started talking about the Bohr model up here versus the quantum mechanical model. And what you're going to see here is that when you look at the quantum aspect of the Bohr model, we're going to use that. Why? Because the quantum model is just too complicated. So because of the complex nature of quantum mechanics or quantum physics, we will not draw energy levels from quantum. But those of the Bohr model. And the question is why? Because they're just more complicated to draw.